So in 14 we are describing the various characteristics of the Watson-Crick double helix model for DNA. And in class we had talked about several characteristics that we wanted to remember. And let's see, what are those? We want to remember that, where's my pen? Okay, we want to remember that DNA is comprised of two polynucleotide chains that form a right-handed double helix. So we have one chain right here, and these are chains of deoxyribonucleotides, and another chain right here, and we said it forms a right-handed double helix. And let me see, and we have that diagram from class. Let's see if I can paste that in here. Nope, not that one. Come on, copy. Okay, there we go. Okay, now what is this? So on the left here we have a right-handed double helix. So what is this thing right here? Where is my pen? Okay, so this right here, this is a thumb. Okay, it kind of looks like a worm, but nope, it's a thumb. So, and if you were to grab a double helix, so over here it's not, the molecule is not drawn as a helix, but in reality the strands form helices, and it's a double helix. And this is a hand, and it's wrapping its hand around the helix, and the fingers are on the two strands. See, they're touching the strands. And if you do that, if you point your thumb in the direction of the helix along its axis and wrap your hands around it, if your fingers touch the strands right there, if you could do that, if your hand was small enough to do that, and wrap your fingers on the strand, so touch the strand. If your fingers are pointing up towards your thumb, then it's a right-handed double helix. So if you try that, and when you wrap your hand around the strands of the helix, if the fingers end up pointing down towards your wrist, well, then it's a left-handed double helix. And that's just one way to tell the difference between a right-handed and left-handed double helix. So let me get rid of all that if I can. Okay, so two strands and a double helix, a right-handed helix. Okay, so that's one thing we wanted to remember. The second thing we need to remember, so A forms 2 hydrogen bonds with T, and G forms 3 hydrogen bonds with C. So adenine base pairs with thymine, and guanine base pairs with cytosine. We have 2 hydrogen bonds here and 3 here. So nitrogenous bases of both chains lie flat and perpendicular to the axis. So what does that mean? Okay, I think the best thing for that is to take a picture, and we'll take one from our book. Let me see here. Okay, here we go. So if the axis of the DNA is like going this way up here, see how the bases are flat? This is kind of like a 3D sort of image, right? There's some shape here, and these guys are flat relative to one another and perpendicular to this axis, and that's what we mean by flat and perpendicular to the axis. So we also know they're anti-parallel, right? Let me see, is that the next one we want to do? Yes, the 2 polynucleotide chains are anti-parallel and complementary. So this is another good picture for that. So anti-parallel means these sugars right here are going in the 5' to the 3' direction for one strand, and the reverse direction for the other strand. So they're anti-parallel to one another. So each turn of the helix is 34 angstroms, or 3.4 nanometers, and includes 10.4 base pairs. So we have another diagram from our book. Let's take that. Let me cut this out here. Okay, so one complete turn. Let's see, what do we mean by that? Well, let's watch this point right here on this strand right here. We're going to follow this around one time. So it went all the way around one time, and that's 34 angstroms, or 3.4 nanometers. And there should be 10.4 base pairs in there. So Watson and Crick thought it was 10. More accurate measurements later, after they first discovered or characterized the model, suggested to be 10.4. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. And here, you know, this is just a diagram. There could be errors in the diagram, but whoever made this diagram was, you know, pretty accurate. So there's at least 10 base pairs there. So that's what we mean by 10 or 10.4 base pairs per turn of the double helix. The diameter of the double helix is 20 angstroms, right? And we can see that right there in the figure. And a major groove alternates with a minor groove. So let's take a look at that. So here's a major groove right here. And you can kind of follow this major groove around, right? If you were down there as small as the helix and you were kind of walking around this path right here, well, you'd just be going around the major groove. And you could also go, you know, this is the minor groove right here. So let me trace the major groove with this red pen here. So here's the major groove. I'm going around the major groove, and you know, this is kind of fun here. I lost track of it. No. Okay, now let's go in the minor groove. So now I want to follow the minor groove. So here I'm just wrapping around here. Okay, well, I didn't really wrap, did I? It's kind of hard. Okay, yeah, so major groove and minor groove. And those are the essential characteristics that we need to know of Watson-Crick's model of double-stranded DNA.